Our sun is a colossal ball of hydrogen and helium 330,000 times the mass of Earth. But the sun doesn't just form the center of our solar system. Every second, thanks to the nuclear fusion reactions in its core, it generates a gargantuan 386 trillion joules of energy, 175 quadrillion of which reaches the Earth in the form of sunlight. And it's this radiation that provides pretty much all the energy we use as humans on Earth. It underpins food chains, drives the weather systems we use for renewables, and of course, it's sunlight captured by ancient plants long buried in the Earth's crust that we're still utilizing when we burn fossil fuels. But what if there was a different way to power our modern industrialized society? What if, instead of relying on photons that have made their way through 150 million kilometers of space, we could create the nuclear fusion reactions that keep our sun burning to grant us an unending source of clean and efficient power? What if we could make a star on Earth? I'm Alex McColgan, and you're watching Astrum. Join me today as we delve into the heart of our star and find out if we truly ever could unleash its power on our planet. Humanity, it seems, has a power problem. Even as we burn through our dwindling fossil fuel reserves and climate chaos intensifies all around us, every year our energy requirements rise by an estimated 1 to 2%. The need for a clean, efficient, and inexhaustible energy source has never been so acute. For many decades, this has been the promise of nuclear fusion. Unlike nuclear fission, which splits rare and unstable isotopes to generate power, fusion technology aims to replicate the processes that happen inside our sun, fusing hydrogen into helium and releasing a huge amount of energy in the process. Yet, since fusion was first talked about as a serious contender for energy generation in the 1950s, it has become a cliché that is perpetually 30 years away from becoming reality. So why then does it seem that fusion is always just out of reach? And do the new private enterprises that have recently entered the field really offer any hope of shaking things up? To begin to answer these questions, there is no better place to start than the place that inspired fusion science in the first place, our sun. As strange as it sounds now, at the turn of the last century, we didn't know what powered the sun. The source of the heat and light that sustains all of life on Earth was a mystery. The leading theory was that the sun's energy came from gravitational contraction. Simply put, the idea proposed that as a star gradually radiates energy to space, it cools and so collapses further under its own gravity, which in turn causes gravitational potential energy to be converted into heat in the star's core. Today, we know that is a genuine process. Not only is it involved in the formation of stars, it's also the reason that the gas giant Jupiter radiates more energy to space than it receives from the sun. In fact, the planet is shrinking by about 2 centimeters every year under its own gravity. And as the resultant internal heat works its way from deep in Jupiter's interior and out into space, it drives the intense storms that dance across the planet's surface. But when it comes to powering a star, one scientist realized that contraction didn't stand up. In a 1920 paper, physicist Arthur Eddington wrote, "If the contraction theory were proposed today as a novel hypothesis, I do not think it would stand the smallest chance of acceptance." He argued that contraction would be hopelessly inadequate for powering a body that radiates as much energy as our sun. Suspecting that stars were places in which hydrogen atoms were cobbled together into heavier elements, Eddington proposed a different source of energy, drawing on experiments carried out by fellow scientist Francis Aston. Aston had shown that the mass of a helium nucleus was ever so slightly less than that of 4 hydrogen nuclei. So if a helium atom was just 4 hydrogens fused together, some mass was missing. Eddington believed that this missing mass was converted into energy by Einstein's E equals mc squared. And because c, the speed of light, is such a large number, the energy generated from even a tiny amount of mass is huge, meaning fusing hydrogen into helium would provide more than enough energy to power the sun. Eddington's ideas were bold and unproven, but they soon inspired serious theoretical work, and in 1929 the first calculations of stellar nuclear fusion were published by Robert Descourt Atkinson and Fritz Houtemans. It turned out that the Sun and all stars were giant fusion reactors, taking the most common element in the universe, hydrogen, and fusing it into other elements, starting with helium. Now, replicating this process on Earth would be hugely advantageous, especially when compared to nuclear fission, the process that is used in nuclear power plants today. Where fission relies on splitting large and rare unstable isotopes such as uranium-235 and plutonium-239, stellar nuclear fusion relies on hydrogen, an element that is widely available on Earth through the electrolysis of seawater. And unlike the radioactive byproducts of fission that create a huge disposal problem for modern nuclear power stations, the byproduct of stellar fusion is helium, an extremely useful element. Thanks to its exceptionally low boiling point, helium is used to cool the magnets in MRI machines, for scientific research projects like CERN, as well as in the production of microchips. It's an essential element that we actually need more of. So how exactly do stars achieve this alchemy of fusing hydrogen into helium? And how are scientists going about trying to replicate the process? Well, the first thing to consider is the reaction medium, the stuff stars are made of. Unlike matter on Earth, stars aren't even made of atoms and molecules, where negatively charged electron clouds orbit positively charged nuclei. Stars are so hot that electrons can escape atomic orbits entirely. The resulting soup of charged particles, ions, and free electrons is known as plasma, and it's in plasma that nuclear fusion can take place. Now, plasma is by far the most common material in the universe, making up well over 99.9% of visible, that is, non-dark matter. But we are part of the 0.1%, that small amount of matter in the universe that's cool enough that in general, electrons confined to orbitals and chemistry, not nuclear physics, dominates, allowing cool balls of rock covered in oceans of water like Earth to form. For us, creating such conditions, making plasma that's hot enough to sustain fusion and containing it, is a considerable challenge. You see, the Sun has one quite literal giant advantage on its side. It's so huge that the force of gravity holds the plasma in a near perfect sphere, with pressure at its core reaching 150 grams per centimeter cubed, so dense a teaspoon would weigh close to a kilogram. The biggest fusion reactor on Earth, ITER in France, a leading international project that hopes to be operational in 2034, will use just a few grams of plasma material in a chamber of 830 cubic meters. Because it's under such low pressure, meaning particles aren't squeezed together like they are in the Sun, this plasma has to be much hotter to achieve fusion, 150 million degrees Celsius as opposed to 15 million degrees at the core of the Sun. Now, fairly obviously, you can't just hold a material like this in a container made of normal matter. If it contacted the sides, it would cool. Electrons would condense into atomic orbitals, and it would no longer be plasma. And of course, it goes without saying that the container itself would be damaged beyond repair. So the plasma needs to be isolated in a vacuum. Two approaches have been put forward to achieve this, the first of which is magnetic confinement fusion. Because plasma is a soup of charged particles, positively charged ions and negative electrons, it can be manipulated by magnetic fields. Magnetic confinement takes advantage of this by using a ring of powerful magnets to hold plasma in a continuous donut-shaped blob in which fusion can take place. There are a number of different types: stellarators and reversed field pinch devices, but the leading design is called the tokamak. This is the type of reactor which will be used at ITER. In contrast, inertial confinement fusion, the other confinement method, takes its inspiration from thermonuclear bombs. It works by firing lasers or projectiles at a small pellet containing fusion fuel, seeking to create temporary blobs of plasma which release fusion energy only for a few nanoseconds before the plasma dissipates. Both of these approaches are immense engineering challenges, requiring either huge amounts of continuous electricity in the case of MCF, or even larger pulses of electricity drawn from banks of capacitors in the case of ICF. But not only do the huge amounts of power involved put tremendous strain on components which have to be replaced frequently, it means that for a reactor to be viable, the energy obtained from the fusion reaction must exceed the colossal amount of energy required to initiate it, a considerable challenge. Something that's pretty challenging these days is finding time for a doctor's appointment. I know a lot of you feel the same. Family, work, people relying on you. You tell yourself, I'll get to it later, and then later never really comes. But thankfully there is a simpler way. ZocDoc, today's sponsor, is a free website that helps you find and book high-quality doctors across all 50 US states. You can book in-network appointments with more than 150,000 providers across more than 200 specialities, from dermatology to dentistry, at a time that's convenient for you. Even better, you can choose whether to see a doctor in person or through a video call. That's why ZocDoc's verified patient reviews are so reassuring. They help you feel confident you're booking a doctor people already trust. Appointments made through ZocDoc typically happen fast, often within 24 to 72 hours, and sometimes even the same day. When you're ready to book, you can see their real-time availability and book instantly. So if you've been putting something off, go to my link zocdoc.com/Astrum space and book your appointment with a top-rated doctor today. And thank you to ZocDoc for sponsoring today's video. With your medical problems hopefully now sorted, or at least on the way to being so, let's get back to the world's energy crisis. As I was saying, fusion reactors take huge amounts of energy to get going. Now you might think, surely once you have surpassed this feat, you've got more energy out than you put in, that would be it, a huge win. After all, the fuel, hydrogen, is both cheap and abundant. But alas, it is not that simple. And to understand why, we have to look back once again at our star and the fusion reactions that only take place deep inside the stellar core. It is here in the Sun's core that hydrogen is fused into helium via multi-step reaction. Firstly, two hydrogen nuclei, or single protons, combine, with one undergoing a process called beta decay to transform it into a neutron. The resulting neutron-proton pair is a nucleus of a heavy isotope of hydrogen known as deuterium. In the next step, another proton combines with the deuterium nucleus to generate a helium-3 nucleus. In the final step, two of these helium-3 nuclei fuse to produce a helium-4 nucleus containing two protons and two neutrons, also known as an alpha particle, as well as two protons. Now, this may sound fairly straightforward, but it's not. The reason being that even in the Sun, getting two protons to react to form deuterium, the first step of the reaction, is far from easy. Firstly, in order to fuse, the protons must get extremely close to each other, around 10 to the power minus 15 meters apart. That is so the strong nuclear force, the force that holds protons and neutrons together in the nucleus of an atom, kicks in, and they are drawn together. However, for two positively charged protons, getting this close means overcoming an immense amount of electrostatic repulsion. So much so that even the kinetic energy provided by the extreme conditions at the heart of the Sun, where protons are traveling around 500 kilometers per second, is wildly insufficient. In fact, protons have only around 1,000th of the kinetic energy they require to overcome this barrier. It turns out the only reason the Sun is able to sustain fusion at all is because quantum effects come into play. Now, you may remember that according to quantum physics, protons don't just act as particles, they also act as waves. This wave behavior means that in 10 to the power 28 proton-proton interactions, the protons can overcome this energy barrier, getting close enough that the strong nuclear force pulls them together. This is called quantum tunneling. But even when protons are drawn together this way, there is yet another effect to contend with. The force that mediates the conversion of one of the protons into a neutron is the weak force, which, because it is controlled by the massive W boson, is very inefficient. This leads to the more likely product of the proton-proton reaction being a proton pair, which immediately decays back into single protons. Together, these effects mean that the rate of proton conversion in our star is extremely slow. On average, a proton will wait 10 billion years before undergoing fusion. Indeed, the only reason the proton-proton reaction proceeds at all is because there are a heck of a lot of protons in the Sun, allowing it to convert 600 million tons of hydrogen to 596 tons of helium every second. This sounds like a lot, but it's actually only a tiny fraction of the hydrogen available for fusion. Now, stopping for a moment to look at the big picture, this is very good news for us Earthlings. It means instead of annihilating itself in a giant thermonuclear explosion, the Sun has been gently burning through its hydrogen stocks for around 4.6 billion years, and will continue to do so for at least a few billion more. It's only because protons are so slow at converting into deuterium that we are here at all. For fusion on Earth, on the other hand, it is bad news. It means the probability of proton-proton reactions happening, where we have much less plasma and much less time, is essentially zero. Indeed, the reaction has never been experimentally measured. In fact, looking at the problem in the most basic and fundamental way, it is statistically impossible to achieve proton-proton fusion on Earth in any meaningful way. So what are all these fusion researchers doing? Why do we even bother trying? Well, they are not attempting to fuse protons. Instead, they are trying to fuse alternative combinations of nuclei that are much more reactive. Back in the 1930s, Mark Oliphant, a student of Ernest Rutherford, conducted a series of experiments. He fired deuterium nuclei at one another, generating other exotic hydrogen and helium isotopes, and thus proving that heavy hydrogen nuclei could be made to react with one another. Today, fusion scientists favor a combination that was first put to use in the H-bomb, one that is 24 orders of magnitude more reactive than protons alone. It is deuterium, remember this is classic heavy hydrogen consisting of one proton and one neutron, and tritium, the even heavier isotope of hydrogen with one proton and two neutrons in its nucleus. The reason this combination is so much more reactive is that these extra neutrons lead to a greater strong force, and there is no need for one proton to undergo weak force mediated beta decay into a neutron. Now, deuterium and tritium aren't just more reactive than the protons that power the Sun. They also give rise to different reaction products. Instead of generating an alpha particle and two protons, They make an alpha particle and a neutron. But like the proton-proton reaction chain, they still produce a ton of energy. Energy that we can use to generate electricity. Just 1 gram of deuterium-tritium fuel holds energy equivalent to 2,400 gallons of oil. So if we've identified more reactive starting materials that give us plenty of energy out, what's the problem now? Well, it's not one problem, but problems. Let's start with those neutrons. Being lighter than alpha particles, they carry most of the energy of the fusion reaction and so have to be captured in order for their energy to be put to use. But controlling a subatomic particle with no charge is no mean feat. Neutrons aren't affected by the powerful magnetic fields containing the plasma and so stream out of the reactor in all directions at 1/6 the speed of light. To deal with this, most reactor designs utilize something called a blanket, a layer surrounding the reaction chamber that's designed to absorb high-energy neutrons and heat up. This heat can then be used to generate steam, drive a turbine, and generate electricity. But this approach is far from perfect. Neutrons aren't just absorbed by the blanket, they ping about everywhere, damaging everything they hit. This hugely limits the lifespan of many components, particularly the reactor walls. Another issue stems from the reactants themselves. While deuterium is relatively common, being easily extracted from seawater, and cheap at $13 a gram, tritium is neither. It has a half-life of just 12.3 years, and the only commercial source are Canada's 19 deuterium uranium nuclear reactors, which produce just 0.5 kilogram of tritium a year as a waste product. Now, ITER estimates that a commercial fusion plant would require around 125 kilograms of tritium a year to run. Current global tritium reserves are around 25 kilograms. And as half of Canada's reactors are due to be decommissioned this decade, this tiny reserve is quite literally going to decay away. But of course, scientists do have a solution up their sleeves for the tritium supply problem. As well as carrying energy out of the reactor, those high-energy neutrons produced by deuterium-tritium fusion can be used for something called tritium breeding. The idea is that you make the blanket surrounding the reactor out of a substance that generates tritium when bombarded by neutrons. The substance preferred by most fusion researchers is lithium, which upon absorbing a neutron helpfully decays into a helium atom and tritium. However, as ever in fusion, this solution comes with its own problem. If each deuterium-tritium fusion reaction generates 1 neutron, which via lithium can be used to generate 1 new tritium, you would need to operate at an impossible 100% efficiency to prevent your tritium supply from dwindling. The answer most fusion researchers favor is to add layers of other elements like beryllium that can act as neutron multipliers, absorbing 1 neutron and spitting out 2. But not only is beryllium toxic, it is also in short supply, and contaminated with uranium, which then bombarded with neutrons, leads to radioactive byproducts, less than ideal. And regardless, there are concerns that even with breeding, most reactors would struggle to generate enough tritium to be viable. So, at this point you might be thinking, hang on a minute. It seems a lot of the touted advantages of fusion, bountiful energy, plentiful starting materials, innocuous, if even useful byproducts, are kind of falling away. Well, you'd be right. We're not fusing hydrogen, or at least the same isotopes of hydrogen that a star fuses, and we're not making just helium, but a bunch of other radioactive products as well. The simple truth, no matter what the headlines say, is that we can't make a star on Earth. And the shortcuts to create something approximating one create a world of engineering challenges. This is why, since the first fusion reactor patent was granted in 1946, fusion has always seemed just out of reach. Each solution comes with a new set of problems. But not all hope is lost. In recent years, things do seem to be changing, with some hugely significant science breakthroughs. In December 2022, for the first time ever, more energy was obtained from a fusion reaction than was required to initiate it, a challenge that had eluded researchers for decades. At the National Ignition Facility, a research-scale ICF reactor in the US, 3.15 megajoules of energy was obtained from a tiny pellet of DT fuel, using an energy input of 2.05 megajoules. Then, in late 2023, the experimental JET reactor in the UK, at Tokamak, generated a world record 69 megajoules of energy from just 0.2 milligrams of DT fuel. And while international behemoths like ITER inch closer to operation, a flurry of private investment has also entered the field, exploring alternative fusion technologies. One is the Massachusetts-based Commonwealth Fusion Systems, backed by Google, Nvidia, and Bill Gates. It proposes using high-temperature, superconducting magnets to produce a more compact tokamak. CFS claims it will have a commercial plant online by the early 2030s. Another outfit based out of Washington State, Huzian, believes it is going to get there even earlier. Backed by the likes of Sam Altman, this company has taken a completely new approach to reactor design. It fires 2 rings of plasma together at 1,000,000 kilometers per hour to generate fusion conditions, a sort of halfway house between magnetic and inertial confinement. This approach allows them to react deuterium not with tritium, but a reactive isotope of helium, helium-3, doing away with the problematic tritium entirely. The use of helium-3 is key to Huzian's approach, because instead of producing an alpha particle and a neutron, these reactants generate an alpha particle and a proton. Vitally, this means there is no neutral particle whizzing off out of the reactor carrying all the energy. Energy is retained within the plasma itself. As the reaction proceeds, the energy generates an increase in internal pressure and a change in magnetic field, which can be used to generate electricity directly. No Victorian steam turbines involved at all. So, what's the catch, you might rightfully ask? Well, just like tritium, helium-3 is incredibly rare, and also has to be bred, this time from deuterium-deuterium reaction, and this process does generate those pesky reactor-damaging neutrons. One of Huzian's proposed solutions is to separate the two reactions, having commercial plants that will use deuterium helium-3 and feeder reactors specifically for generating helium-3 that have planned shorter lifespans. But there is another issue with deuterium helium-3. This mixture requires much higher temperatures and fuel densities than conventional deuterium-tritium fuel. Huge pulses of electricity are needed each time the reactor fires to generate fusion conditions, which puts immense strain on electricity supplies and reactor components. It's a considerable engineering hurdle for Huzian to overcome as the company embarks on building its first commercial-scale reactor. But CEO David Kirtley claims this plant will be online and supplying power to Microsoft data centers by 2028. Now, whether or not this comes to pass, only time will tell. However, even if none of these private ventures hit their well-publicized milestones, the fact that this investment exists at all reflects the moment the fusion sector finds itself in. With new algorithmic and AI tools now at their disposal, for many in the field, it does feel like fusion is finally inching closer to reality. And though unsolved scientific and engineering problems exist, regardless of the approach used, the diversity of fusion technologies that now exist is a huge bonus. So, while we'll never be able to recreate a star on Earth, it is very possible that the one or even several of the approximations we are trying to build will play a pivotal role in the energy landscape of the future. I'll end by returning to Eddington, and his 1920 musings on the energy powering stars. A star is drawing on some vast reservoir of energy by means unknown to us. This reservoir can scarcely be other than the subatomic energy, which, it is known, exists abundantly in all matter. We sometimes dream that man will one day learn how to release it and use it for his service. The store is well nigh inexhaustible, if only it can be tapped. Maybe finally, it won't be another 30 years until we find out if it can. We are nearly 1,000 members on Patreon, and it's so exciting to see our community grow. If you want ad-free videos, wallpapers, and to join a community of hundreds that love space, sign up below so we can finally reach 1,000. It's more than a number, it's a milestone for everyone who's been part of Astrum's journey. Each new astronaut makes this constellation bigger, the conversation deeper, and the experience richer for everyone. So if you've been watching from the sidelines, now's the perfect time to join the community.